Okay, so you're welcome back to episode 14 on the series, and just want to say that the last episode went down really well. It's amazing how such a simple thing can get so many views. Like the spark plug is a fairly simple part, but I think overnight it got in the last 12 hours it got something like 5,000 views. So it just goes to show that sometimes it's the simpler parts that get the most views. I mean, what I would call far more interesting videos like the torsional damper or the pneumatic valve train part, over time has got a lot less views, but that's just the way it goes, I guess. So in this episode, I will be covering the Formula One push rod. Now, I want to do this mainly because I'm bringing in a lot of carbon fiber parts in the next while, and I just want to give all the viewers a bit of a primer on how carbon fiber works for a start, how it's made, what it looks like, and why it's used. So I know a lot of you will have worked with carbon fiber before or have seen it, but in terms of parts which really matter, there's a few things that normal carbon fiber, which would be parts that you buy for your car or parts that you buy for your bike or even parts that you buy for your home. Like for example, there's carbon fiber bats going now. Um, so they kind of differ in terms of parts which are critical, which would be aerospace parts or Formula One parts. So I just want to bring you up to speed with that first before moving on to far more complex parts in terms of manufacture and layup, which would be critical parts on a car, wishbones, crash structures, the monocoque, spoilers, intakes, various parts like that. So I think this is probably the best place to start in terms of introduction to carbon fiber parts and layup. Now, one thing I will say, or sorry, a few things I will say with this video. It's going to be pretty long. You're going to have to concentrate. It's not a lie back and just listen video. You have to sit up and watch this to understand the videos that will follow on carbon fiber, because it's going to be a fairly quick uh, introduction into carbon fiber cloth types, layups, weights, how it's manufactured, and all that sort of thing. The second thing I will say is there's a huge storm after moving in here. As you know, some of you know, I'm in the west of Ireland on the Wild Atlantic Way, and there's a gigantic storm after moving in. So if I do pause the video or say that I have to pause the video, it's just because the storm has got fairly severe, and it'll get pretty loud in here because I've got a lot of skylights. It's making hail. The winds are, I think, 100 kilometers an hour. So if I have to pause it, I will, but hopefully I shouldn't. The third thing is my hands are diabolical this evening compared to normally. They're normally pretty bad. Um, so what I do with these videos is I come out to the workshop after the day job. I do a bit of tinkering around with maybe the bike or the car or with other stuff. Then I do these videos. So my hands do be in a state normally. Um, but this time, because I was cutting up carbon fiber and machining various parts, they're particularly bad. So just excuse that. It'll be fine, but that's just the way it is. These videos, as I said before, they're never going to be polished videos of, I remember saying to a guy in a comment there recently, I'm never going to appear in a shirt beside a Ferrari 430 Scuderia. It's just not going to happen. They're hardcore engineering videos, uh, parts you've never seen before, details you've never heard of, possibly, hopefully, and this is just the way it's going to be. So it's going to be a bench, the parts, and that's kind of how it's going to go for the next while. So we'll see how it goes. Um, Again, if you're feeling generous, the link up top there, buy me a coffee link. I should probably change to buy me brown paper link because I'm going through quite a lot of it of late with various drawings and dirt. This one has been here since the previous video, so I want to hang on to this. But yeah, up there, uh, buy me a coffee. It goes to support the channel, pays for parts, pays for cameras, mics. I hope to buy a new camera soon because the phone just isn't cutting it. As well as that, the microphone is on the way. Um, a lot of you, as I know, have been complaining, or not complaining, but just saying that the sound isn't spectacular. So hopefully the new mic will improve that. Now I've exported the last video in mono, so for headphone users, it should be appearing in your right and left channels just instead of the left channel. I have no idea why that is, but that's that. So again, the push rod. This push rod is from a Honda. Now it's an old enough part, but again, it's a good place to start. There's push rods in all cars, you know, up to current day. Now some of them can be push rods or pull rods, and I'll cover that first. So if I just go through the differences between a push rod and a pull rod, we can move on to the part. So if you're looking at the back of the car, say this is the nose, you all know this, but I'll draw it anyway. So that's the monocoque there at the front, the tub. This will be the wheel, the left-hand wheel. This is the lower wishbone, this is the upper wishbone. And if I draw it in a push rod configuration, up to here, up to the rocker, and the damper then would be here, that would be the spring. So that's a push rod configuration. As the wheel goes up, it pushes this push rod here and it compresses the damper through the rocker, and there's a spring on that as well. So that's fairly straightforward. Now in the pull rod configuration, which is not as common, it'll be the same thing. Monocoque there, wishbones, wheel here, but instead the rod will be going like that. So when this goes up, it pulls this rod, and the damper and spring would live in here. So that would be the spring. So nowadays, just because of the shape of the car and with aero, it's normally the push rod configuration, because with this configuration here, it's quite tight for the driver's legs. I mean, the pedals will be here, so there's very little room in there for that. Plus as well, with just the new developments in aerodynamics, the nose of the car would be quite low here. That would be the spoiler here, or the front wing. The car would slope up here, the wheel would be here. So you haven't really got room for this damper here. I mean, it would be going down into the airflow here, the plank would be here, and there just isn't room for it. So now this system is nice because the damper is lower in the car, it's a lower center of gravity, but with the new modern aero, there just isn't room for it, and it has to live up here on top. So you've all seen these pictures in plan view. The front wing will be here, and the dampers then would live here, the left and right damper. There will be a rocker here, which will pivot here, and then the push rod will connect to that, which will be this arm here. So that's kind of it. Now the reason these dampers and spring assemblies are inboard is because if you put them outside here, like a normal, let's say a normal car, if you had them, oh, I don't know how you could draw this, let's just pretend you had them here, and the spring would be here, they would be all in the aero. So that'd be really bad, and slow down the car. So they're moved inboard, and they're out of the aero, so the car can go quicker. And these push rods, which I have on here, are shaped in a aero profile to cut through the air. So that's a basic rundown. Now you can obviously go off and read all about push rods and pull rods yourself. In the early days, these were made from steel. They were probably a 41, 30 or whatever grade. An aero profile, which would be fabricated like this, like that shape. You're all familiar with it, like an airplane wing kinda, and the end of it then would be tapered in. You'd cut it, the end would be like this. You would cut a slot in there, you'd make two radius pieces here, and you'd weld in a tube there which would have a thread in it, and you would then tap in a rose joint. So that's how the early ones were done. The good thing with steel is, compared to carbon fibre, you can do a very easy inspection on it with crack testing where the welds are. With carbon fibre, it's not so easy. It needs pretty much all the testing and scanning you can do. I know with the Dreamliner, the latest aircraft, whatever model it was, manufacturer, I think that fatigue testing and examinations are a bit of an issue, because carbon fibre tends to be harder to scan for cracks or fatigue. So you have to give it everything. You have to X-ray, CT scan, and all those sort of scans. With metal, you can just do a basic, it's been around for ages, a developer, you spray on a developer, or even, which was done in the early days, you'd spray on just a paraffin, just plain paraffin oil, which you would use for lanterns or for heaters a while back. Spray on paraffin onto the part, wipe it all off, spray on talc, or even like baby powder talc, like that, and just warm the part gently, and you would see the paraffin then would creep out of the cracks, and you would see it wetting the talc areas. So that's kind of, in the really early days, how they did crack testing. Now, like nowadays, you can get just developers you spray on with the chalk. There's a viscous solution you spray on first, and then a chalk, you wipe it off, warm it up slightly, and then spray on a chalk developer, which shows you the cracks. Now I have actually developers here which I'll show you in a later video, but that's kind of the difference between metal and carbon fibre. Now obviously carbon fibre is lighter, or can sometimes be lighter, but it's just a lot stronger. So we shall move on to the carbon fibre part now. Now, I know a lot of you have seen carbon fibre parts online or have made them. You've bought them for your cars, your bikes, carbon fibre seats, mud guards, roofs, bonnets. Now the problem with all those carbon fibre parts is, while they are made fairly well, they are not a structural part, which is where this part differs. And something you don't really see online or presented is structural parts, or how they're made. It's very easy to make a part which looks lovely. Carbon fibre, very cool. Wow, I've got a carbon fibre roof in my car, it's brilliant. Everyone looks at it, takes pictures, fantastic. It's light. You'd see a lot of carbon fibre roofs. I think BMW, the M3 CSL came with a carbon fibre roof, just for lightness. But again, not a structural part really, and it's kind of just a vanity thing. But in Formula One, the parts have to be structural, obviously. So this is a wishbone here. You can see the cross section. I'll just bring it up just roughly to show you quickly first. So that is the cross section. So that would live, let's put it the right way. So that would live like that. So you've got your trailing edge and your leading edge here. This cuts through the air, and then it slopes in, so you have no vortices, and it just sails through the air like that. But this part is made out of very different carbon fibre fabrics than your normal carbon fibre parts. So let's have a look at those now. Now I have got the microscope set up here, so we'd have a really close look at the different weaves, how it's laid up, and the tooling to make it. Now with this, you can see the shape of it there. There's a void in the middle. Now this void is created with a vacuum bag or a pressure bag, depending on which way it's made. But there's generally, I'm going to say 3 or 4 types of weaves. There's a unidirectional weave, which would be the center part here for strength. Now I'll get to that in a minute. And then there's twill weaves on the outside here. Now with carbon fibre layups, the most strongest way you can have your fabric, or you can lay it up, is a unidirectional weave, which will be the carbon fibre going all the same way, like that. So in tension, this is very strong. They're all going the same way. They're all in tension. Fantastic. So you can see it here like this with these aluminium rods. They're just TIG filler rods. So I can show you why or how these work with the unidirectional fiber. Now unidirectional you'd never see in parts you would buy online for your car, because they don't look that pretty. They're just plain black, nothing fancy. They don't look like this. So people rarely see them. They're not that exciting, but they're a core fabric in Formula One for strength. So I can just do a simple demonstration here now. So if you've got unidirectional fibers, which would be just like this, straight, now obviously they'd be, you know, a lot thinner. And if I put these under tension, these are fine, fantastic, as strong as they can be, all in the one way. The force is traveling all in the one way. But if I put them in compression, you can see they buckle like that. Now that isn't great in a push rod, as you can imagine. So what's needed in a push rod is a combination of unidirectional fibers, which make up 75% of the push rod. Keep in mind, carbon fiber is fantastic when it's in tensile, where there's a tensile force put on it, but in compression it's not that brilliant. So the epoxy resin between it is actually keeping them all together in compression, and is adding to the binding effect of the fibers. So if we just pretend this O-ring here is the epoxy resin holding them all together, we can slide it on there, and when I put them now in compression, you can see, even though this is very weak, like it's a very weak O-ring, they're really held together. They don't buckle. You can even see in my hand there, they're making an imprint, which they didn't before. So it really strengthens them. Now, to go on from that, which you'll see here, is this pattern here, which you're familiar with on cosmetic carbon fiber parts, which you've all bought, I'm sure. Wherever there's unidirectional carbon fiber strands like this, they tend to wrap them in a twill weave, just to keep them contained like this O-ring does. So in a moment I'm going to bring in the microscope and show you all the different layers on this part, how it's made, and where the strength comes from. So as mentioned, this is the unidirectional fiber, fantastic in tension, not so great in compression. So we need something to keep them together. So that force which keeps them together is the epoxy resin and a twill weave over them. Now it's important to note as well that with carbon fiber, I mean, you've seen a lot of projects, I'm sure, online which involves which I would call dry carbon fiber, where you buy the roll, like a roll of fiberglass, and you mix up the resin, you put it onto the mold, you wet the mold, you put a release agent on the mold, you wet the mold with epoxy, you put the fiber down, you're like you would make a fiberglass boat or a fiberglass wing for a car. You then pour more epoxy on it, you wet it out, and you keep going with layers and layers and layers. Now this is not great in terms of structural parts, because you have no way of controlling how much epoxy resin you have in the carbon fiber matrix. Now ideally, if you're doing a wet layup, which that is called, you want the ratio to be 1:1. So if you've got a square meter of, let's say, 2x2 twill weave, dry weave carbon fiber, you want, which would be like 2x2, a standard 2x2 would be 220 grams per meter squared. So you also want the resin weight for 1 square meter of that twill weave to be 220 grams. So you'd have the carbon fiber to resin ratio of 1:1. Now, obviously, as we know, the main strength in a carbon fiber structure is from the carbon fiber itself. So the less resin you can have, the better. But the problem with doing a wet layup in carbon fiber is you're not going to easily wet out carbon fiber to a 1-to-1 ratio with that much resin. I mean, 220 grams of resin isn't that much. You're going to have your hands full trying to wet all the fibers, and if you don't succeed in wetting all the fibers, let's just pretend these fibers are wetted out, they're all one unibody now, but these aren't wetted. They can float in the breeze, so to speak, so they're not really doing anything. So it's pretty hard to get a structured part with a wet layup, which is why, I mean, you know, it's not done at all with structural parts. With aerospace or with Formula One parts, wet layup is it's considered amateur. Even here, if I have to do prototypes or rig up something for a company, you would never use wet layup. You would always use pre-preg. Now, pre-preg carbon fiber is a sheet of carbon fiber which would start off as dry, but they vacuum impregnate a resin into it, which would be only approximately 35%, because you can control it so easily with in factory conditions. You can wet the carbon fiber fabric, you can vacuum it off, you can make sure they're all wet, and you then freeze it, which prevents the epoxy resin from drying. So you can get a far higher carbon fiber to resin ratio with pre-preg. Now, obviously, this isn't really, you know, it's not something you do as a hobbyist or DIY. It's kind of a professional item. You would buy it from a company. It would come frozen. It's generally wrapped in tin foil and in insulated packaging. And once you receive it, you would have to freeze it to continue to keep the epoxy in a non-reactive state. And once you then take it out of the packaging, you start laying it up, it starts to go off, so to speak, and you can then bake the part and set the resin. So that would be the main difference between, you know, a wet layup and what I call a professional pre-preg epoxy fabric. So just to look at the fabric types, I just bring in another bit of brown paper for a moment, and we have a clean sheet, so to speak. So again, the primary type of carbon fiber weave would be what's called a plain weave. Now, a plain weave, would you believe it, isn't something you'd see very often, which would resemble this. Now, I'll explain it in a minute when I have it drawn. So a plain weave would look like this. So as you can see, one weave would go over and under, over, under, over, under, over, under. And the alternating layer at 90 degrees to that would be the same, over, under, over, under. Now in plan view, this would look like a chessboard, exactly. So if you looked at it under the light, it would look like a chessboard, black, white squares. You know, it would be exactly, what would you call it, symmetrical. Now, the problem with this sort of weave is it's extremely strong in that this is the shortest path and these ones are the shortest path in the, let's say this is the X and the Y direction. Now, the more common weave is like this. I probably should have drawn these before I started the video, but as I said, these are all live, seat of the pants. So, this is a more common weave. You get the idea. So this weave is called a 2x2 twill weave. Now, you'll notice that this weave here goes over two of these strands. Now these strands are comprised of many fibers. There might be 5,000 carbon fiber strands in each of these, let's call them cables or threads. So it goes over two, goes under one, goes over two, goes under one, and continues on like that. Now in plan view, this will look exactly like this part here. So if I just zoom in, you can see, hopefully, let's bring it over here. I might have to put the microscope on this. Let's see. So you can see this weave here. I may bring the microscope down in time. It's actually going over 2 weaves this way, which will be the same as this here. Now, why did they do that? This weave here is generally done on flatter parts. It doesn't generally conform that easily to complicated compound curves, such as organic curves on a car bonnet or a wing or something like that, because there's a lot of friction between this strand here and this strand here. They lock up quite easily, so the fibre isn't going to comply as well. So you're going to have a hard time bending that into a sharp corner. If you had a mould like this, the fabric would have a hard time bending in there, conforming in there, without having an air pocket here and looking terrible, and obviously being weaker as well. So that's why they use this fibre more commonly. There is a distance here, which is in the spec sheet of the fibre. That distance there then means how sharply you can bend this fabric, in that they can both move when this starts to tighten here around this fibre here in the Y direction. These 2 strands here can move closer together, so they'll be able to conform, and the fabric can be a little elastic that way, whereas this one can't, because they all lock up on each other. So this distance here, you can buy various different 2x2 twill fabrics where this distance is specified, and the wider this distance, the sharper the corner of this fabric can bend. So that's kind of the main rundown on fabric types. Now obviously, again, you can get another fabric which would be like this, where you'd have 4 here and 1 here. Now, I know for a fact this is called a 4x4 twill weave. I know from being in the Pagani layup shop that on the A-class surfaces, which would be there's different class surfaces on a car, on all cars, not just carbon fibre cars, but on normal road cars as well. There's the A-class, the B-class and the C-class surfaces. Now, with a car, the A-class surfaces are the surfaces you see when you look at the car. So that'll be the bonnet, the wings, the mirrors, the wheels, the dashboard, everything you see when you sit into the car. The B-class surfaces then would be door shuts, the bonnet shuts, I don't know, the glove box shuts, all that sort of thing. And then the C-class surfaces would be, you know, underneath the bonnet, underneath the seats, in the boot, all that sort of thing. So in Pagani, in the layup office, which I visited, they use exclusively 4x4 twill for the A-class surfaces on the Zonda R. So this will, it's a nice fabric, it conforms well to organic surfaces, and it looks well. So what I'm going to do now is pause the video, and we'll move on to the Wishbone part, set up the microscope, and we'll have a look at exactly all these fibres. The one fibre I didn't draw here actually before I just stopped the video is the unidirectional fibre, which is just that. There's no weave, it's just fibre all going in one direction, like the wood grain in a piece of timber. So very strong in one direction, but not so strong when it's subject to different forces. So I'll pause the video, bring in the microscope, have a look at the actual part, and I'll see you in a sec. Okay, so just one more thing before I bring in the microscope and show you the PushRod up close. There's a lot of talk, or there, you know, in designing carbon fiber structures or monocoques or pushrods, but it's actually quite simple. Now, I don't mean to disregard composite layup engineers, but it's assumed that it's a black art with a lot of people in terms of layup and and carbon fiber choices and that sort of thing, different fabrics, but it's not actually that complex. There are computer softwares out there that lay out carbon fiber. Each one comes with a spec sheet. The As I said, the single direction, like this carbon fiber here, is the main one that's used, because if it's not that much different to a tubular space frame chassis, which you've all seen. You've probably built race cars with tubular chassis, like 4130 tubular steel, coped and TIG welded together. Carbon fiber behaves exactly the same way, just that each of these are tiny tubes. So you can lay out your car, like if you were to make a small, a toy car, or let's call it a matchbox car or a dinky car. If you wanted to design the perfect car with box section, let's just pretend it's aluminium sections here for the chassis rails, and you wanted to put in carbon fiber shear panels here, riveted or bonded onto them. So that would be one carbon fiber panel. This would be the other, because there's a load going up here to the rear wheel, and let's just pretend this is the front of the car and this is the back of the car here. Because these would be shear panels, this load here would go up. Same with this. So you would put your biaxial fiber here like that, and this one here like this, same as you would with a tubular structure, space frame structure. When this wheel tries to go up, these carbon fiber strands are then in tension, which is what you want. This wheel tries to deflect here over a curb or a speed bump or whatever on the track. Same again. This rectangle here tries to convert into a parallelogram, so these fibers will be in tension, so you would put the layup that way. So again, this is your most useful layup if you're talking structural components in a car, or in various suspension components in a car. That's your go-to carbon fiber fabric. These ones are just to prevent buckling. It's just to keep them contained, and so that's how you would lay it up. Now obviously it will be a different number of these. If you've got a force, whatever, if you look at the car in plan view, very simply, this is just very elementary stuff in a car. In plan view, if you had your tub like that, let's just divide it down the middle and across here. Again, for torsional rigidity, you would lay this that way, that one that way, this one that way, and this one that way. And as the angular torsion of the tub itself would try and deflect, you're putting these strands into tension. So you want to keep all carbon fiber, if you're laying it up, into tension. It's not so good in compression. It relies a lot on the epoxy bond in compression to keep them together, and the 2x2 twill weave to stop them buckling. But that is the general law on layups. As I said, there is computer programs to lay out all the different strands. They come with spec sheets, so your tensile modulus of every layup. There's many layers obviously, but that's very basic on how you do it. So let's bring in the push rod itself and have a look at it and see the different layups. So let's get rid of that and get more brown paper. Nearly through a roll now at this stage. So open the link, buy me a coffee, buy me brown paper, well needed. So this is the push rod. It's a Honda item, as said. I've had this part for a long time, and I think it was one of the first parts I bought. So it's pretty, in terms of meaning to me, it means an awful lot. I'll never get rid of this part. It was a part I bought, I think, about 13 years ago, 12 years ago, 10 years ago, I can't remember. But it's when I properly started doing, I had started a whole lot of research, engineering research, before I bought this part. But it was the first part I bought. It was a cheap part, I think it was £20. And it got me well into the way of being able to write online, how to conduct yourself online, how to project yourself to peers, and it went down very well. So it's really important to me, this part. It means a lot, and it will never leave here. So if we bring in the microscope and the laptop, thankfully the microscope is now working because we've got no crazy voltages of spark plugs. Hopefully there's no glare. I'll have a glance. There's a tiny bit of flicker, but that should be okay. So I'm going to be steering the microscope here on the part. You're going to be looking here, and we should hopefully be okay. So we're having a look here at the twill weave. Now I'll bring back this for a second, which I crumpled up, which you shouldn't. So as I said, the 2x2 twill weave, one skips, there's one here, it skips two, there's one, skips two, and one again. So you can see this very clearly here. So let's call this the X, and this one is the X, and this one is the Y. So you can see this weave here, it jumps over this one here, and it jumps again, which is this one here. So it's jump two. So that is a 2x2 twill weave, which is fairly common. So that is the outside of the part. Now on the inside, we'll bring in this. Now I have to keep an eye on the screen for this. Yeah, perfect. So on the trailing edge of the push rod, you can see on the end here, things are very small here now, so you have to have patience. You can see the 2x2 twill weave. There's many layers here. Because this is a high energy stressed area, both front and the back, this will be the rear. They've got many layers of 2x2 twill weave on the rear edge and on the lead edge. You can see on the nose there, there's many layers of 2x2 twill weave all along there, and they finish here, and again on the top they finish here. Now the very black layers which you can see there are the single direction carbon fiber, which, as mentioned before, is good in tension and compression if it's contained with 2x2 twill weave, which it is. Now also on the external part of this, let me see, can I just pull the mic around on all of it, which I should be able to do. Focus. There we go. So around the entire perimeter, there is also a twill weave, which is this weave here, which contains all of the fibers. Now it's very hard to see it because it's only one layer, but it is there just around the outside. Let me try and focus. Yeah, perfect. So you can just see that layer there around the outside, just a very faint white line. So again, that is the twill weave, which contains all the single direction, the biaxial fiber in the middle, which is black. Now there is one layer there which is 2 by 2 again, just as an intermediate layer, which keeps it all together. And on the inside here is 2 by 2 again. Now I'll show you how this is made in a sec, but that's the general layup. So high energy areas, there's 2 by 2 there. Again, these layers are very thin. You know, they're only, I think they're 0.002 millimeters wide. So excuse the fumbling on the microscope. You see on the trailing edge they're the same. They come into about 15 millimeters before the biaxial weave starts. They just encompass it all and keep it all contained to stop it buckling. So that's that. This part here is about 3 millimeters thick, approximately. So hopefully you can see that there well. So let's move on to how it's made, and then we'll go on to how the inserts are put into it. Now this push rod here would be, which way would it be? It would be this way. So the wheel would be here. This has been cut obviously. This would extend up the rocker and onto the suspension dampers. So this part here is titanium. It's been titanium nitride treated. As you can see, the gold color. It's common in a lot of parts. You probably have seen what would you have seen it on? Cobalt drill bits. They're gold. It's just an anti-galling or an anti-fretting coating. Now let's move on to that in a second. I want to show you how it's laid up first in the mold. So what I do now is pause it, move on to the mold, and I shall talk to you in a sec. As I said, it's going to be a long video, but there's a lot to go through, and I just want everyone to be primed on what has to follow in terms of carbon fiber parts. So I'll talk to you in one sec. So in terms of how the push rod is made itself, so there would be a pattern made of the push rod. Now if I just draw how they would lay it out or how it's done. So with modern methods, they can just machine a negative of the push rod. So it would be done on a plate like this. Half of the push rod would be on the plate. The plate would look like this. This is very rough, but it'll give you an idea. And the bottom plate then would be, this would be the top plate. And the bottom plate, tooling plate, would be here. This would go around here, up here, and over here. So they're the two tool plates they would require for making the tooling pattern for the pushrod layup. So they would machine these normally from whatever, either tooling board like this, or in most cases aluminium. It would be just a cheap aluminium like 6.0, like a 6.0 what, 6.3, whatever. So they would then take this tooling plate and lay up what's called, again, pre-preg carbon fiber. Now you'd see a lot of people again online in the hobby market or in lesser critical components. They would either pour a tool on here with a polyurethane tooling resin, or machine it directly from this, which is tooling board. But in terms of highly stressed parts, you generally want this in aluminium because it has to go into the autoclave. So they would machine this from aluminium and they would lay up a tooling carbon fiber pre-preg on here. So many layers again of just a non-cosmetic, non-functional pre-preg tooling carbon fiber, lay it on there. They would then do what it's called, if you're laying up carbon fiber, you have to do what's called a debulk, which would be compressing the fibers or the layers down as you go. So you would lay up a maximum of 5 layers, debulk it with a vacuum bag so that they all squeeze down, pack tight together, lay up more layers, debulk that again, and then put in the autoclave under vacuum. So the debulk just gets them all to conform tightly as you go onto the tooling shape. So you would warm them up. Again, this is frozen as it's coming out of the shipment package, or as you take it out of the fridge. This is fairly strong. So you would, if you've seen them on YouTube, they apply a heat gun or a hair dryer just to soften the resin a small bit. They push it in with the plastic tools like that. You see them rubbing it in like that. That's just to get it to conform. As it comes up to temperature, it gets a debulk, more layers, debulk again, and then it goes into the glaive. Now the reason they use carbon fiber here and not tooling board or aluminium is because you ideally want the tool which you're making the push rod in, you want that tool to be the same material as the part you're making, simply because in terms of expansion rates, when you're like the kiln or the oven is quite hot, the autoclave is quite hot, so they all have to expand together, and they tend to keep the same expansion ratio of thermal coefficient and all that. So that's why they use carbon fiber as the tool. So if we move on and try and do a rough layup here, this is going to be very rough, but it should give you an explanation with masking tape. So let's just have a glance at the camera. Yeah, perfect. So if we use masking tape, just to show you how the tool was laid up. So when these tooling pre-pregs are cured, you've got, obviously this will be a lot wider, but this is the shape you want to make. This will be carbon fiber and probably about 7 millimeters thick. So there'll be a lot of tooling pre-preg. There might be 30 layers, and it would then be bolted together. But that would be the shape you'd be left with. Obviously this is the shape of the approximate shape of the push rod, which we're talking about here, very roughly. And so what they would do first is lay up the 2x2 twill in here like that, and that will be to there. Now this would be cut off here with a blade, and here with a blade, so that will be flush here. And they would then lay up many layers. I won't go through them all, but there would be many layers of the single direction weave put in here in the middle. Loads of layers. Loads. And so on. Now in the top of the tool, it'll be the same thing. Now obviously this is very rough. So you would lay in your 2x2 twill there again. That will be cut off flush. Many layers of the biaxial in here. Here. And here. And that will be the basis for the part. So this would be, at this point, this would be about the same thickness as this here. And they would then, before they close the mold, they would lay up the 2x2 twill on the leading and trailing edges. Now I want to keep this kind of short because you hopefully get the idea from the microscope shots a minute ago. So again, this is 2x2. This is biaxial. And over that, they would put a 2x2 twill. Like that. Now on this part here, the top, there wouldn't be that. There would be just a 2x2 twill weave here on top of all the biaxials to keep them together. Now when they're putting the tool together, it's literally like this. It's not the most neatest or what would you call it? I don't know, neat process. It's pretty much, you know, not that tidy when they're doing it. So this is what it looked like. These are all sticking up here. These are sticking up here. This is flat. They would bring this down here, and just let me zoom in, or not zoom in, but just check how it looks. So these will then be bent in. Remember, these are still quite frozen. So if you bend them in, they will stay there. Again, if you bend these in, they will stay there. So they bring the tool together. This would bend in. Remember, these are 2x2 twill weave. These are bent in. Let's just bend them down there. And the tool goes together like that. And they form the joint between them all, as do these ones at the trailing edge. When that is done, or sorry, before that is done, they would put in a bag here, which would be like a bicycle tube. Now, depending on the part geometry, you could either put this under vacuum or under pressure. So the manual would either expand or it would be sucked tight to the part, which would compress all these layers in here and join them all together. This is then put into the autoclave under pressure and heat, and it is put in there. Generally, it depends with the carbon fiber prepreg. Normally it's put under, it's generally ramped up to 20 degrees first, and it's soaked at 20 degrees for approximately an hour. Then it's brought to, I think, like, it depends with all the different carbon fiber parts or with fabrics. It's brought to, I think, 180 for about 9 hours. It's then ramped down to 50 degrees for an hour, and then it's taken out. So it's a fairly long process. It's a costly process as well, because you have to keep the autoclave under vacuum, under pressure. When it's taken out, the part is then taken out, and we should hopefully be able to peel this out here. Possibly not. Maybe we should. And just stick that on there. Peel this out of the tool. That will be stuck on there. There will be a release agent put on the tool here as well, and you've got your carbon fiber part made. So that's how that works. Again, not something that's covered with DIY carbon fiber layups, or not covered that much online, because just because it's not that interesting in terms of aesthetics, but structural parts generally aren't. So that's how the push rod itself is made in terms of the carbon fiber layup. Now if we look at the insert into this here, as I said, this was done with a titanium part. When the part is made, actually, this would be a lot wider. This part, it would go on here for, you know, for the length of the push rod. Now what they do is, if you can imagine that as the cavity in the tool for the push rod, they would normally put a little witness mark here, which would be, it would be machined a little bit deeper here, and then it would extend off here for the vacuum bag or for the bladder or whatever you want. And this line here would show them where they have to cut the push rod when it comes out of the tool. So the push rod would have a witness mark here where it has to be cut. That's their datum line. Obviously it would be fixed on a jig then again for further datums when you're placing these parts, but that's how they get the datums. They just put a small little witness mark on the tooling here, and they know where the part ends. But in terms of bonding then, this part, as said, is titanium, the gold part, titanium nitrate coated. This face here would have spacers, shim spacers, in order to do the stack up where you want to preload or get dimensions right. Now, this bolt here, as you can see, is threaded, as is this. So this bolt here would locate into this one here, and there would be a spacer here which locks off there, and the whole lot clamps in on that. Now you will see a small thread here. Now in some cases in the past I've seen where before the bolts are put in, this threaded portion here, which you should be able to see there, yeah, they put a nozzle here and they can inject the adhesive in here, goes up here, and it will flow out here and flow out here and here as well and here as well, and they can then put in these screws here. So that's a nice way of getting resin into the interference joint. Now this resin here is made, I think, by Henkel, or either Henkel or Heysel. I think it's probably Henkel nowadays, but this resin, which I'll bring in on the mic in a second, is a normal epoxy resin which is charged with glass beads, which lightens the resin and just allows it to keep what's called the bond line tolerances, which I'll show you now on the microscope. So I'll bring in the laptop and show you that. So again, looking at that one, there's a flicker now on that. That should be okay. So if we bring in the microscope to look at that bond line, now again, remember you're looking at the screen, not what I'm doing. Yeah, perfect. So if you look at that bond line, you can probably see the resin has got a lot of voids in it. Now I would imagine after scanning this part failed and didn't go into service because there's just so many bond lines which have voids in them, which isn't good, as you can imagine. So you can see a void there. Now you will see the epoxy is kind of like, I don't know, it's got bubbles in it there, the glass beads. So that just lightens the resin. And the diameter of the glass beads also serves as a compression limiter, in that if you put in that insert and you put it in too tight there in that direction, which is the vertical bond line, the glass beads will set the diameter and the width of the bond line and prevent it pushing out all the adhesive. So that's why you would use epoxy, or sorry, glass beads. So let's go on here. Now if you can also see, let's get a pointer. Now diameter, or sorry, dimensions are very small here. So let's try and get a pointer in there. Hopefully we can. One sec. Let's go in from this side. Yeah. So if you see that bond line there, which is black, now you're probably wondering why this is black. There's the epoxy bond line and there's the carbon fiber. This bond line here, if you're bonding either aluminium or titanium to epoxy or to anything else, it's extremely hard to get a proper bond line on the titanium, because titanium and aluminium form an oxide layer which doesn't really grip epoxy too well. So what they do is they cover the part with epoxy. Let's go in there again, which is that black line there. They then sand that part with the epoxy on it. So the epoxy creates its own atmosphere, which shields it from oxygen, which stops the part from oxidizing, and you get a proper bond line. So this part would have been, first of all, sandblasted, coated with epoxy, sanded, which prevents the oxygen getting at it, and then you've got a proper bond line, so you can bond again, secondary bond, when you're putting it into the part. Now this is pretty hard to show and describe because it's just so small, but hopefully you get the idea. So that's kind of that. Bring it up to the camera again. You can see the part there. They're the voids, which are not good. That's, I would imagine, because there's no taper on this part here, it would be very hard to get that clean of a line. So I would imagine that the insert was coated with epoxy. The wishbone was coated with epoxy. Once it's machined, you can see where it's data machined there to accept the insert. Because this is an organic and random finish inside, once it's made, it's machined out. This is glued up, for want of a better word. So is the insert. It's inserted in. They put a nozzle in here into that M4 thread, pump in more epoxy. It extrudes out here, and it's then bonded. So pretty cool. And again, if I just swap it around here, you might be able to see if I just put my carbon fiber filled hands around it, you can probably see the 2x2 twill weave on the trailing edge there, which will be here. And again, the 2x2 twill weave on the leading edge, and just where the tool comes together. So yeah, that's that. So again, this is just a primer on carbon fiber parts, which I'll be covering a lot more of in later episodes, but it's just good to get you up to speed with how they're done, how it's made, the different carbon fiber types, and hopefully that should cover it and get you psyched for the next ones. Alright guys, thanks a million, talk soon.